Now I'll get on with this radical business. We have this times this, which multiplied together gives you 16, and that simplifies to be 4. The next one can be seen in different ways. Now some of you guys just look at this, oh, that's a root 3 and a power. Those are inverses of each other. They undo each other. That's fine. You can do that. I'm going to change this root 3 to be to the 1/3 power since we just practiced this. Really quick, if I have a third root of 5, the 5 has a power of 1. And remember flower power? The power is what goes on top of the exponent fraction. And the root, which is the 3, goes on the bottom. So I have 5 to the 1/3 power. What do we do with parenthesis exponents? We multiply them to inside exponents. And so we have 1/3 times 3, which is 5 to the 3 over 3, or that is just written as 5 to the 1, which is just 5. The next one, this one's a little different. Actually, I guess it's not that different because it's just an x. It is an odd thing, just like the letter B right there. Let's just do the same thing. X to the 1/3, and then I'll multiply it by a 3. Whoops. No, it's actually the opposite. The 3 goes on the x because that's the power. Oh, and then we have the 1/3. Oh, we still get the same thing. It's still x to the 3 over 3, which is x to the 1. So we just get x for that one. And then finally the last one. This one's the weird one because, let's see, we would just go and put the power on there, and then we have the 1/6. And then we would, get y to the 6 over 6, which equals y to the 1 power. So we just have y. But this answer isn't sufficient. The reason why this answer isn't sufficient is because y cannot be negative. Let's pretend y was a negative. If y was a negative, we would go negative y times negative y times negative y times negative y 6 times. And we would do all this inside of the even root. Now the problem with this is the even root. You can never have negatives inside of an even root. You can't find the square root, which has a 2, which is even, in having a negative inside of it. You can't have a negative inside of a square root. You can't have a negative inside of a 6th root either. Yeah, but when we multiply this, it becomes positive. No. See, the way what I just wrote means I can also write this. And actually, that's not true. You can never have a negative inside of an even root. I don't have to write all of them. I think you get the point. We can't have a negative inside of an even root. So what we do to say that we can never have a negative inside of it is we make this y to be in absolute values. So don't forget what this means, people. Don't forget what this means. If you had a 5 raised to the 6th power, and that was in that, the 6th root, this has to be, well, I mean, I guess that's kind of redundant because the absolute value bars just make it positive and it's already positive. But we can't have a negative inside here. That's not allowed. Let's simplify some radicals. Now when you're simplifying radicals, you're looking for perfect, well, it's not cubic or quadratic, anyways. You're looking for something that's being raised to the 4th power. Something that's being raised to the 4th power will give you 48. And actually that's not possible. Nothing raised to the 4th power will give you 48. But is there another number out there that when raised to the 4th power will give you 48? Well, what is 2 raised to the 4th power? What is 3 raised to the 4th power? Let's just write those ones really quick. 2 raised to the 4th power, 2 times 2, that's going to be 4. Then you have to multiply by 2 times 2 again. That's going to be a 16. So 2 raised to the 4th power is 16. 3 raised to the 4th power, that's the same as 3 times 3 times 3 times 3. This and this are 9. This and this are 9. So 9 times 9 is 81. So here is a perfect 4th power, and this is a perfect 4th power. And those, actually 16 happens to go into 48. So we can split this up to be the 4th root of 16 times the 4th root of 3. And the 4th root of 16 is 2, so I can write 2 4th root of 3. Let's look at the next one. The next one is a square root. Yay! Alright, what perfect square divides 25? Dang it. I mean, what perfect square divides 75? It's 25. And that would be times 3. Now what about this x to the third power? Well, I can split that up too to be a perfect square inside. I'd be left over with an x. X squared times x is x to the third, and I can split it up. This guy and this guy are going to simplify to be 5x, and then the 3 and the x are going to stay inside the square root. That's how you simplify that dude. Alright, here's a funny looking one. We have a root and a power that are the same. So what does that mean? That means 5x. Like they cancel out. But don't forget the absolute value. Because we have an even root and power, because they're even, you have to do this. If those were odd, you wouldn't have to do the absolute value bars. We'd be done. Now we know that 5 is always going to be positive, so we can take the 5 out. And your answer would be like so. Alright, let's look at some odd ones. Let's see, something raised to the third power that would give me 24. Oof, I don't know. Let's go. See, 1 to the third power is 1, 2 to the third power is 8, 3 to the third power is 27. Oh look, 8. 8 goes into 24. Let's do that. So we have the third root of 8. 8 times what? 8 times 3 gives you 24. So since 8 is a perfect cube, we just write 2, third root of 3, and we leave it. Very good. Okay, the next one. We have a third root again. Hey, we have another 24. We already know this 24. We were used to him before. We have third root of 8, and we have third root of 3. Now what about that a to the fourth? No problem. We have the third root of a to the third, and then we have the third root of a. This guy and this guy are going to simplify to be 2 and then a, because we have an odd exponent. I'm sorry, an odd root and an odd exponent. We don't have to do the absolute value thing. Then we have the third root of 3 and then a. Bam. Finally, the last one. Oh, we got a negative inside there, but that's okay because we have an odd root. Yay, odd roots. You can always have odd roots inside of or negatives inside of an odd root. Let's take, for example, our friend the 8. If I had this, that would be a negative 2. Why? Because negative 2 times negative 2 times negative 2, that would equal negative 8. So I'm looking at this negative 40 and I'm recalling, hey, negative 8 divides that. And let's look at the x to the 6 at the same time. Let's do x to the, wait, x to the 6, yeah, that works because x to the 3 and x to the 3, and those are both perfect cubes. And so then we also have to have that 5 in there because 5 times negative 8, that gives us the negative 40. So these are going to cancel out. That's going to simplify because they're all perfect cubes. We have 2, negative 2, and then x and x, which is just x squared. We could have just left it like that. And then the square root of 5. Alright, so that's how you would simplify that one. Another way to do this, oh man, how come I didn't think about this before? Another way to do this is with, oops, that's supposed to be a 6, is with a rational exponent. We have a root of 3, and that's the same as 1/3. If we distribute this to the exponents, we would get negative 40 raised to the 1/3 power, and then we would have x to raise to the 6 over 3. This simplifies to 2, x to the 2, which is what we got earlier. But then we have this, and then we're going to end up doing the same thing, the same kind of thinking that we did up here when we split up the negative 40 into a negative 8 and a 5.